Welcome back, Chemistry 30. This is the next video in the MS2.2 section. So we left off with dispersion forces and saw that if I increase the molar mass, which means increasing the number of electrons that an atom has, I'm increasing the polarizability of it, which means more electrons could collect on one side for a moment in time, making that side negative, making the other side positive, and of course inducing a dipole in a neighboring molecule. So increasing molar mass would have an increased boiling point due to those increased dispersion forces that exist. Okay, so that was dispersion forces. Now we'll look at two more. The first one being dipole-dipole attractions. So these are ones that are charged, just like the temporary dispersion ones, but they have permanent dipoles. So these are polar molecules, ones that have a large difference in electronegativity, lending to itself of one side being negative, the other side being positive. And of course, how this one would work, the positive end of one molecule is attracted to the negative end of another, and vice versa. And these forces are important when molecules are close to each other, so they can attract with that opposite sides attract. So here's some examples. Here we have a liquid held close together by permanent dipoles. And of course, the more polar the molecule, the higher its boiling point. So the larger the difference in electronegativity, making big polar bonds, it would have a higher boiling point because it would be more difficult to separate them when going from a solid to a liquid or from a liquid to a gas. The strength of the dipole forces increases with increased polarity, obviously. So that's pretty easy to understand. A permanent dipole, obviously there'd be an attraction. Now something interesting happens when we look at this case, but before we do that, which has a greater effect, dipole-dipole or dispersion? So you may think, well, I kind of mentioned that dipole-dipole were stronger than dispersion, but what happens though in terms of molecule size? So if the two molecules are of comparable size and shape, so if they're similar in size, then dipole-dipole would be the dominating force. So if the molecules are in similar size, the ones that I'm comparing, obviously dipole-dipole would be more. But if we have one molecule which is much larger than another one, okay, then dispersion would likely be the dominating force of attraction that's going to exist there. Okay, so that's something interesting to recognize and remember. If they're very similar in size, dipole-dipole interactions are going to be the dominating force. Whereas if we have a larger molecule, yes, those random electron movements are going to overtake anything else. Okay, so we have, so if we can, and this trend works, but there's some inconsistencies here. So for example, if we look here, CH4, SiH4, GeH4, SnH4, what's the difference between all of those? So we can see they're all bonded to 4 hydrogens, carbon, silicon, germanium, and tin. Carbon, silicon, germanium, and tin. So you can see we're going down a group here. So as I go down a group, the boiling point increases because we have more electrons that could randomly move around, making it more difficult to separate them when going from a solid to a liquid or a liquid to a gas. If I look at so this is a group 4. So this is group 4, 4A. Let's look at ammonia. Now something interesting happens here. NH3, where are we at here? Okay, this path, let's be careful here. So it follows this pattern right here. So this is what I'm looking at next. NH3 going to SBH3. So NH3 to SBH3. Now they didn't write the other ones here, but this would be PH3, and this one would be ASH3. It's kind of difficult to squeeze it in there, but it follows the pattern here, but something weird is happening here with the nitrogen. So PSH and SB, PAS and SB follows the pattern, but for some reason nitrogen is higher, which is kind of weird. So that is, let's see, that was group 5. So group 5A. Let's look at another group here, HF, going all the way to HI. So I don't know how we're going to distinguish this one from another one. I'll maybe make it a blue color here. So there we go. So these ones go together. And again, so HF, so we have HF going down to HI. So HF, so we'll have HCl, HBr, HI. So this one here would be HCl, and this one here would be HBr. Follows the pattern here, but again, one that would have a small molar mass, such as fluorine, is actually a stronger dispersion force. Lastly, H2O. So we're comparing the H2O, H2S, H2SE, H2TE, as you see over here. So let's see, this previous one was group 7A, so this one here is group 6A. And again, follows the correct pattern here with H2S, H2SE, H2TE, but again, so these three here are interesting. When I'm dealing with those and H is bonded to one of those, they are quite high in terms of dispersion forces. So now why is that? So as we can see, most of it follows the series, but the polar series follow the trend as seen on the graph until you get to the smallest group. So when H is bonded to an O, F, or N. O, F, or N. So that leads us to the third type of bonding. And I like to call this hydrogen bonding is FON, is FON. Because when H is bonded to an F, O, or N, you get a really strong attraction force there. So the dipole-dipole interactions experienced when H is bonded to an N, O, or F, or I like to reorder it FON, are unusually strong. And of course, you may have a prediction made already. The reason why is because, if you recall, F is extremely electronegative. So when it's bonded with H, it's going to basically pull that H to its end more often, making a really negative side. And that's true with N and O. They're relatively high in the electronegativity scale too. We call these hydrogen bonds. It is now let's highlight this. It's the attraction between hydrogen atom in a polar and non-bonding electron bond pair in a nearby atom. So if we take a look at this, so when I have H bonded to a F, O, or N, that's when we have this happening. So if I have H bonded to O, of course I'm going to have two H's there. I have water. And what happens here is that the H side is positive. The O side is negative, so I'm just making those little delta symbols, right? Delta, H plus, H plus. Now the bond here, the hydrogen bond, occurs between H and a lone pair of electrons. Intermolecular forces, because it's outside, whereas here we have our intramolecular force inside. So it's the H of one molecule attracted to the lone pair of a F, O, or N type molecule. H bonded to F, same thing. Lone pair of electrons, H, attraction. H bonded to N's, there we go. H is going to be attracted to the lone pair of that end. Then I can mix these up. Have an N group, an H bonded to an N, and an H bonded to an O. Look at that. H is attracted to that lone pair in the N. Or over here, H is bonded to that lone pair in the O. So as long as I have one molecule that has an H bonded to an F, O, or N, and it comes close to an F, O, or N in a neighboring molecule, which doesn't necessarily have to be bonded to an H, I get this hydrogen bonding happening. Hydrogen bonding arises in part from the high electronegativity of N, O, or F. The hydrogen atom has no inner electrons, therefore the positive side of the dipole has the concentrated charge of the nearly bare hydrogen nucleus. So the only thing that's left, if the other atom, the F, O, or N, is taking hydrogen's electron, all that's left is a nucleus, which is positively charged. And that positively charged is attracted to the negative charge of the neighboring molecule, which contains an F, O, or N. All right, I think we'll stop there and we'll come back to the next one.